Before going to the next simplex algorithm, that is two phase method, last time we were doing the big M approach. In the big M approach, what we were doing? We have to introduce the artificial variables for greater than equality constraint and also equality constraint, and we were imposing a big penalty which we were introduced as M, and ultimately we were trying to eliminate. Let us solve one more problem. We have not done that part using equality constraints. Let us consider a problem, maximize z equals twice x 1 plus x 2 plus thrice x 3 subject to x 1 plus x 2 plus twice x 3 less than equals 5 and 2 x 1 plus 3 x 2 plus 4 x 3, this is equals 12, and x 1, x 2, x 3 are greater than equals 0. If you note it, in this case you will find that here we do not have, although the greater than equality constraint, but we have one equality constraint, that is the second equation. So, to write it in the standard form, first we have to convert it the LPP into the standard form, maximize z equals objective function will be x 2 plus 3 x 3. I am writing the other part later, subject to for this one x 1 plus x 2 plus twice x 3 plus we are introducing x 4 and this is equals 5. The next equality constraint 2 x 1 plus 3 x 2 plus 4 x 3, here x 4 will not be there, but to get the initial basis we have to introduce one artificial variable, that is x 5, and this is equals 12. So, here it will come 0 into x 5. So, that this portion becomes the identity matrix and we will get the initial basic variables as x 4 and x 5. So, here with this variable 0 into x 4, since x 5 is the artificial variable, therefore, one big penalty is being introduced and it is becoming minus m into 5 x 5, where x j is greater than equals 0, I is equals to j equals 1 2 like this way 5. So, your initial BFS will be x 4 equals 5 and x 5 equals 12 and other variables x 1, x 2, x 3, this will be equals to 0. Now, as usual we have to now form the initial table and from there we have to start the iterations. For this one you see this table, I think it is clear or no. So, your variables are x 1, x 2, x 3, x 4 and x 5 and corresponding coefficients of C B, here it will come B as, here you have only 2 A 4 and A 5, x 4 and x 5. Value of B from here if you see it is 5 and 12. Value of the coefficients of the objective functions are 2, 1, 3, 0 and for the artificial variable it is minus m. So, that for C B it will be corresponding to x 4 it is 0, corresponding to x 5 it is minus m. Now, let us write down the coefficients of the constants, that is it will become 1, 1, 2, 1 and 0, then it becomes 2, 3, 4, 0 and 1. Directly you are writing from these two constants as usual. So, I think it is all right. So, now we have to calculate the z j minus c j. As you know, z j minus c j is c b into x 1 plus c b into x 2 minus c j. This is actually your c j, z j minus c j, this will be your c j. So, it is minus 2 m minus 2 for the first one 0 into 1 minus 2m minus 2. So, this is minus 2, the next one similarly it is minus 3m minus 1, the next one is minus 4m minus 3, then it will be 0 and the next one is 0. So, therefore, most negative one is this one, therefore, entering vector will become x 3. Now, you calculate the ratio, that is b by x b. So, b first one is 5 by 2, next one is 12 by 4, that is 3. So, the minimum of these two is this one, therefore, your outgoing vector is x 4 and your pivot element is this one. So, as I know, in the next iteration what we have to do? We have to make these two as 1 and this coefficient as 0 and we have to rewrite this one. So, the basis now becomes A 4 will be out from this table and A 3 will come over here. So, it will be A 3 and it is A 5. So, x 3 and x 5, your not C b, C j, C j is 2, this remains same 21300 and your C b now becomes 3 corresponding to x 3 3, this is minus m. So, now if first one we divide the first row by 2, so that this pivot element becomes 1. So, just I am writing after dividing by 2 half half, this is becoming 1 half and 0. Now, for this one, this minus 2 into this, so that this becomes 0 and like this way if you compute for all you will get 2 0 1 0 minus 2 and 1. Now, you can calculate again the z j minus C j from here, z j minus C j is 3 by 2 into 0 minus 2. So, basically it is minus half, the next one will be minus m plus half, the next one is 0, next is 2m plus 3 by 2 and 0. So, again most negative is this one, that is x 2 will enter into the basis. So, we have to calculate the ratio for this one is 5 and for this one is 2 by 1. So, it is 2. So, outgoing vector will become this. So, you will get this table now. So, pivot element is this one, this is already 1. So, your x 5 is out and x 3 will enter into the basis. Now, so in the next table, from here we can form the next table again. In the next table from here, if you see your C j is same, your this is 2 1 3 and your x 4 is 0. Since x 5, here you note one thing, in the last table your artificial variable x 5 is out from the basis. Once it is out from the initial basis, therefore, we may drop the table, drop the column corresponding to x 5 also. If you see this table here, we have written up to x 1, x 2, x 3, x 4, whereas it was earlier x 1 to x 5. So, if artificial variable is out from the basis, then we can drop that particular artificial variable also. So, now here your b will be a 3 and a 2, this is x 3 and x 2. So, corresponding to this will be 3 1. Now, it is a routine matter, that is as usual you have to do it. This column I think will remain the same, because 1 was the pivot, 0 minus 2. In the next column I am not explaining, because now it is a routine matter, the same way we calculate the table 3 by 2. So, if you calculate now z j minus C j, z j minus C j will become minus half 0 0 5 by 2. So, still z j minus C j is less than 0, therefore, the pivot element is x 1. Now, you have to calculate the ratio for this one it is 3, for this one it is becoming infinite. So, you cannot consider it. If it is infinite or if it is negative, the ratio is infinite or negative, you cannot consider that case. So, therefore, your outgoing vector will be x 3. So, in the next table again here your initial basis will be, instead of A 3 is going out, A 1 is entering and A 2 is there. So, it is x 1 x 2, C j is 2 1 3 and 0. So, it will be C b will be 2 1. On the same fashion, your pivot element was in this case half. So, you have to make this one as 1 and this is already 0. So, you do not have to do anything. So, on the same way, whenever you are calculating, it becomes 3 1 0 2 3 and 2 0 1 0 minus 2. So, if you calculate Z j minus C j over here, Z j minus C j, you will get the values as 2 plus 0 minus 2 0, like this way. This will be 0, this is 1, this is 2. So, now if you see in this table, Z j minus C j is greater than equals 0 for all j, and Z j minus C j is 0 for the basic variables and Z j minus C j is greater than 0 for the non-basic variables x 3 and x 4. So, you can say that the solution is unique, and the solution you can write down x 1 this is equals 3, your x 2 this is equals 0, sorry x 2 is 2, x 3 is not present in the basis, therefore, x 3 will be 0 and max z, if you just calculate, it will become 8. So, like this way you can solve the problem using the big M method. If you remember, if I have told at the very beginning that the big M approach is good, but it has only one disadvantage. The disadvantage is that whenever you are imposing a big penalty, that is, we have introduced M and we have assumed that whenever I will compare M with any other numeric value, M always will be greater. But if I want to implement it, that means whenever my LPP is very large, number of basic variables, number of constraints are many, I cannot solve it manually, compute it manually. So, I have to take the help of computer. Whenever I am taking the help of the computer, in that case it becomes difficult to determine the value of M. What value should I give for capital M? That is the biggest disadvantage of the big M method, because there may have some value which is greater than M what I have given. For this reason, afterwards another method was invented, which we call as two-phase method. In this two-phase method, basically what you are doing, the procedure what we are adopting in the two-phase method is that in the initial phase, we are not taking the actual objective function, but we are creating one auxiliary objective function, and whatever slack and surplus variables and the original decision variables you take, in the auxiliary objective function we take the coefficient of the variables including slack and surplus variable as 0, whereas whenever I am taking the artificial variable, for the artificial variable we do not impose any big penalty, but we are adding one coefficient, the coefficient as minus m. So, that is the auxiliary objective function, and in the auxiliary objective function, with that function we try to make the simplex table and we go on iterating it. Basically, in phase 1 our basic aim is to eliminate the artificial variables from the basis, or to make the artificial variables value in the basis as 0. If we may not be always able to do it, sometimes you will see that in the iterative process at the end of phase 1 the basis contains some artificial variables, or it may not contain the artificial variable, that I will discuss. So, after the end of this phase 1, actually we take the actual coefficients of the objective function and again we apply the simplex algorithm. So, the basic difference between the big M and two phase method is the penalty used for the artificial variable. Only change is here, In big M approach, you are applying the minus M or a very big penalty you are imposing, but here you are not imposing a big penalty, but instead of that we are just considering a penalty of price of minus 1, and in phase 1 you are obtaining one initial basic feasible solution, and with that BFS you are starting in the phase 2. Let us see the steps of the phases. Phase 1, I am just writing this, it will be better for you. Convert each of the constraints, into equality constraint. Obviously, whenever you are converting into equality constraint, you are using the slack variable, surplus variable and the artificial variables you have to use, otherwise you cannot convert it into equality constant, and this already we have seen earlier. Or in other sense, you are writing the LPP in the standard form. In the step 2, now you are taking a new auxiliary function, objective function, new auxiliary objective function we are taking. What will be the form of this? I am just writing maximize z star. Please note that usually we take maximize z, but this is not equivalent. So, we are taking another function, objective function z star. The form of this will be something like this: 0 into x 2 plus 0 into x n minus 1 into x n minus x, say I am giving x a 1 minus 1 into x a 2 like this way, minus 1 into x a m to denote, to make, where if you see the minus 1, this price has been added for each artificial variable in the coefficients. Here the artificial variables are x a 1, x a 2 and x a m. These are the artificial variables. So, for the artificial variables you are imposing a penalty of minus 1 in the coefficient, whereas for all other variables including slack and surplus variables the coefficients are 0. So, it is 0 into x 1, 0 into x 2, 0 into x n this. Our basic aim is to make, whenever maximize z star, this value will be 0. That means what? That means all the artificial variables are 0, then only your maximize z star will be 0. So, maximize z star equals 0 means all the artificial variable values are 0 in the basis, whereas maximize z star, if this is less than 0, that means less than 0 means at least one artificial variable is positive, at least one, there may be more than one. So, this I have to note, if maximize z star is 0, that means your artificial variables, all the artificial variables are 0 in the basis, whereas maximize z star less than 0 means at least one artificial variable is positive. So, now in step 3 you have to apply the simplex algorithm, whatever we have done earlier. Simplex algorithm you will apply. Some cases will appear here, which I am stating as number 4. Whenever we will end phase 1, when suppose Zj minus Cj is greater than equals 0, then your phase 1 ends. So, the terminal condition for phase 1 is Zj minus Cj should be greater than equals 0. So, you are coming out. Now, 3 different cases can occur. One is maximize Z star, the value of the Z star is 0. It means all the artificial variables will disappear from the basis. All the artificial variables, whenever maximized z star equals 0, all the artificial variables will disappear from the basis and we will obtain basic feasible solution. We will obtain BFS. Okay. So, maximize if Zj minus Cj greater than equals 0 and the maximum of Z star, the auxiliary objective function value is 0. In that case, the artificial variable will disappear from the basis and we will obtain the basic feasible solution of the original problem and we can go to phase 2. Another case may occur, maximize Z star equals 0 and one or more artificial variable appears in basis with, please note this one, appears in basis with 0 value. So, first case is maximize Z star is 0 and artificial variables are not present in the basis, we will get the basic feasible solution. Second case is although maximum Z star is 0, but one or more artificial variable appears in the basis, but their corresponding value is 0. In that case also you will obtain the basic feasible solution, but it may happen that there is redundancy in the constraints. This we will actually discuss in the next class, that how redundancy in the constraints occur and how it affects the simplex tables. The third step is maximize Z star is less than 0. It means one or more artificial variable appears in basis with positive value, since maximize Z star is less than 0. So, in this case I am not writing this, similar to this, but only difference will be it is appearing in the basis, instead of 0 value it will be positive value. So, then only maximize Z star will be less than 0. So, when it is less than 0, one or more artificial variable appears in the basis with positive value. In that case, we will not obtain any basic feasible solution for the problem. So, we do not have to go to the phase 2. So, when I will not obtain any basic feasible solution, if maximize Z star less than 0, when in the final iterative table of phase 1, one or more artificial variable is present in the basis and their corresponding value is positive, no basic feasible solution can be obtained for that one. All other cases you may obtain the solution. So, for these two cases, whenever at the end of the iteration of phase 1 and phase 2, whenever these cases 4a and 4b appears, then we will go for the phase 2 of the system. In phase 2 what happens? You have the final table of phase 1 and we are considering the cases of 4a and 4b only, because whenever maximize Z star less than 0, then no basic feasible solution. So, we do not have to do anything, we do not require to go to phase 2. In this case, actually you are taking assign actual coefficients of the variables. Here I want to mean variables means the including slack and surplus variable in the objective function. So, here basically you are starting with the last table of the phase 1, but there is one change. The change is you are taking the original objective function and in the coefficients of x 1, x 2 like this, you are taking the actual coefficients, say C 1 x 1, C 2, C 2 x 2 plus C 3 x 3, something like this. So, these are the actual coefficients, the table will remain same And now again you apply the simplex algorithm whatever we have done earlier. The only thing to be noted here that if it comes for the second case maximize z star equals 0, where one or more artificial variable appears in the basis with 0 value, we have to be cautious that these artificial variables should never become positive, because if they become positive, in that case we will not obtain the solution. So, then this thing again we will use with the help of examples, we will see how we can solve this problem. Now, let us see how to solve the problem using the two phase method. Let us take the example. I think this is the example. Okay, let me just write down. Maximize z equals twice x 1 plus x 2 plus thrice x 3 subject to x 1 plus x 2 plus twice x 3 less than equals 5, and 2 x 1 plus 3 x 2 plus 4 x 3, this is equals 12, x 1 x 2 x 3, this is greater than equals 0. If you see this problem, I think just now I have done it. The same problem whatever, if you take this one, we have already solved this problem using the two big M method. Now, the same problem we are trying to solve using the two phase method, so that you can understand the difference between these two approaches. So, at first I have to write down the this LPP into standard form using slack, surplus and artificial variable. For less than equals, I have to use one slack variable, whereas for equality constraint I have to use one artificial variable. So, this is, if you try to write down maximize z star, now I am writing this, I will write down afterwards subject to x 1 plus x 2 plus twice x 3 plus one variable x 4, another artificial variable is required. So, I am writing 0 into x 5 equals 5, and for the next one twice x 1 plus thrice x 2 plus 4 x 3 plus x 4 is absent, but this one will be plus x 5, this is equals 12, x j obviously greater than equals 0 for j equals 1 to 5, since we are having only 5 variables. Now, as we have told, we are creating the auxiliary objective function z star, where for all variables except the artificial variables, the coefficients will be 0. So, all variables means here x 1, x 2, x 3, x 4, x 5 is the only artificial variable. So, your z star will be 0 into x 1 plus 0 into x 2 plus 0 into x 3, 0 into x 4 minus x 5. So, you have incorporated this one. So, basically maximize z star equals minus x 5, this becomes 0. So, you see this problem now. In this problem, it was you took the actual coefficients values in the maximization of the objective function, and you introduced a big penalty m for the big M method. And in contrast, in this, in phase 1, you are constructing one auxiliary objective function, where you are putting 0 for all the variables, the coefficients of all the variables as 0 except the artificial variable, and for the artificial variable you are making it minus 1, but the constants will remain as it is. Now, from here you can construct the initial tables. So, just see this one. So, now we are starting the phase 1. Once you have constructed the initial, the standard form with the auxiliary objective function, if you see, this is your objective function. The other things are similar whatever we have done earlier, this is C j. So, here in this particular problem, then what happens? Your basis is x 4 equals 5 and x 5 equals 2. This is the basic variables x 4 and x 5. all other variables x1, x2 and x3 these are 0. So, therefore, here it will come as a5, a4. So, it is x5, x4. In Cj coefficients are 0, 0, 0, 0 and for this one it is minus 1 from this objective function. This already you know it. So, your Cb will be minus 1 and 0. Now, B is 12 and 5, just I have written the other way. So, that the matrix we are writing 2, 3, 4, 0, 1 and next one is 1, 1, 2, 1, 0. So, if you see purposefully I have written A5 first, A4 then, that means order does not matter over here. In the earlier cases we were writing the or first A4, A5 means in order, but in any order you can enter the variables into basis which will not affect, only thing you have to write the corresponding row properly. So, once I have written this, now you can calculate Zj minus Cj using the normal process, that is minus 2, minus 3, minus 4, I am not explaining again. So, the most negative is minus 4, you calculate the corresponding ratios. First one is 12 by 4, that is 3, next one is 5 by 2. So, 2.5. So, this will be the outgoing. So, entering vector is x 3 and outgoing vector is x 4. So, this is your pivot element. So, once I have obtained the pivot element from here. So, here it is your entering vector a 5 remains same, a 4 is out and a 3 is coming out, that is x 5 and x 3 will come out. Zj minus Cj is less than equals 0. These values will remain same 0, 0, 0, 0, minus 1. So, it will be minus 1 and 0. So, I have to make this value as 1 and this value as 0. So, directly I am writing the data, because this is simple calculations, you will obtain this thing. So, it will be 5 by 2, half, half, 1, half, 0 and the next one will be 2, 0, 1, 0, minus 2 and 1. So, corresponding to x 3 we have made this one pivot element as 1 and the other one corresponding to next row as 0. So, we have done this one. Now, calculate the Zj minus Cj using the normal process. You will see that 0, minus 1, 0, 2, 0, still Zj minus Cj less than 0. So, the most negative here is this one. So, x 2 will enter into the basis, x 2 will enter into the basis and which one will go out, that is 2 by 1, 2 and 5 by 2 divided by 5, that is this. So, this x 5 will go out and your x 2 will enter into the basis. So, we form the next table from here. Once we are forming the next table, this is again Cj. So, for the next table it will be x 5 is out. So, a 2 will come, that is x 2 and x 3, this will appear in the table. It is 0, 0, 0, 0 and minus 1. Corresponding Cb obviously it will be a 2 and a 3 is there. So, 0. So, if you see this is already 1. So, this row will remain same, only thing I have to make this element as 0, whatever operation we require we have to do it. So, I am writing again the directly the values 2, 0, 1, 0, minus 2, 1 and the next one is 3 by 2, half, 0, 1, 3 by 2, minus half. So, now calculate the Zj minus Cj. If you calculate it, you will find 0, 0, 0, 0 and 1. So, now Zj minus Cj is greater than equals 0 for all j for this case. So, now we can move to phase 2. since all Zj minus Cj is greater than equals 0. Please note one thing, that this is the final table of phase 1 and in the basis there is no artificial variable. Your artificial variable was x5 and that is out from the basis. So, obviously, we will obtain some solution for this, as I have discussed with you earlier different cases. And if you see if you calculate the value of Zj minus Cj, maximize Z star, that is also in this case will be 0, because the last one also it is 1 minus 1. So, it is 0. So, now come to the phase 2 of this one. In phase 2, you will start with this table only, initial table is this, but as I have told you, you have to take the original objective function now. That means, now you have to take maximize Z equals twice x 1 plus x 2 plus thrice x 3 plus 0 into x 4, this one. So, you are taking the actual coefficients for the objective function. Here one more thing you should note, that in the last table you had 5 variables including the artificial variable x 5. In this one, since in the basis x 5 is not present, so in the first iterative table of phase 2 I have dropped that column for the artificial variable, since it is not necessary. So, basic aim of this two phase method is, if possible, eliminate the artificial variable at the end of phase 1, and then at the beginning of the phase 2 you start with the original objective function and try to iterate and obtain the basic feasible solution. So, the table will remain same as usual, A2 A3 x2 x3. If you see this one, this table, these values will remain same. So, I am writing just those values, that is 2 0 1 0 minus 2, and this one is 3 by 2 half 0 1 3 by 2. Only change will come in the Cj. In Cj, in the last table the coefficients was 0 0 0 0, but in this case you have to take the actual coefficients of the variables. That means, now you will take 2 1 3 0, and so corresponding to x 2 1, corresponding to x 3 3. So, compared to the last table of phase 1, the changes are like this. In Cj, you are taking the actual objective coefficients of the decision variables in the objective function, and since Cj has changed, so your Zj minus Cj will also change. So, now again calculate the Zj minus Cj, you will find these values. So, once I am obtaining this, Zj minus Cj is negative, therefore, entering vector is x 1. So, you have to calculate what is the outgoing vector. This is cannot be taken, this one is 3. So, only 1 is there, therefore, your x 3 will be the outgoing and this is the pivot element. So, still you have to continue with the process. So, instead of A 2 A 3, A 2 will remain there, A 3 is out and A 1 is coming, that is x 2 and x 1. So, now again this is your Cj. So, 2 1 3 and 0. So, you make this as 1, this is already 0, you do not have to do anything. Your Cb is 1 and 2. So, I am writing this one 3 1 0 2 3 and this is 2 0 1 0 2. If you calculate Zj minus Cj, you will find Zj minus Cj values are coming like this. So, therefore, if you see Zj minus Cj is greater than equals 0 for all j. So, we will stop here and we have obtained the basic feasible solution. Again note one thing, Zj minus Cj equals 0 for the basic variables here x 1 and x 2 and Zj minus Cj greater than equals 0 or positive for the non-basic variables x 3 and x 4. So, we can say that the optimal solution is unique. And what is the solution? Solution is from the basic variables we will obtain x 1 equals 3, x 2 equals 2, x 3 is not present. So, x 3 is 0 and z max is equals to 8. So, basically if you compare the same problem whatever way we have done it for the case of the using big M approach, here number of iterations are little more, but it is assured that if solution exists you will obtain the solution. That means computationally whenever I will try to implement it using computer, it becomes very efficient for us to develop this one. So, for that reason two phase method is most important. So, I think it is clear how we are doing the phase 1 and phase 2 of the methods. Let us take 1-2 more problems of different types. One is say maximize z equals 3 x 1 plus twice x 2 subject to twice x 1 plus x 2 less than equals to 3 x 1 plus 4 x 2 greater than equals 12, x 1 x 2 greater than equals 0. So, this I have to first convert it into the standard form with the auxiliary objective function. So, since 1 greater than equality is there, I have to introduce one artificial variable and for this case one more variable is required. So, I am writing maximize z star subject to, let me write down this one first, twice x 1 plus x 2 plus x 3 equals 2. For the second one 3 x 1 plus 4 x 2 then minus x 4 since it is greater than equals plus x 5 this is equals 12, x j greater than equals 0 for j equals 1 to 5. So, here we are using the incorporating surplus and artificial variables. Maximize z star, the coefficients of all the variables will be 0 except the artificial variable. So, 0 into x 1, 0 into x 2 plus 0 into x 3, 0 into x 4 minus 1 into x 5. So, this is your initial standard form for the phase 1 of the two phase method for this problem. So, I think it is okay now how to calculate the find the auxiliary objective function and from there come to the objective initial BFS of the phase 1 iterate through and then if it accepts you go to the phase 2. So, for this problem for phase 1 what happens, your this one will come, this is not required, this is actually C j. Your basic variables obviously are x 3 and x 5 only. The basic variables here again x 3 and x 5, x 3 equals 2, x 5 equals 12, all other variables x 1, x 2, x 3, x 4 they are 0. So, I am writing a 5 and a 3. So, this is x 5 and x 3. The values of the coefficients are 0, 0, 0, minus 1. So, it is minus 1 and 0. From here it is b value is, if you see from here it is 12 and 2. So, you are writing here 12 and 2 corresponding rows you write down now the coefficients, that is 3, 4, 0, minus 1, 1 and 2, 1, 1, 0, 0. Once you have done it, now calculate the z j minus c j. So, it is minus 3, minus 4, 0, 1, 0. So, most negative is this one, that is x 2 will be the entering vector. So, calculate the ratio 12 by 4 it is 3, 2 by 1 it is 2, minimum is this. So, outgoing vector will be the x 3, right. So, now let's proceed to the next one. Here it is x 5, the artificial variable still present here, x 2 is this. So, it is a 5, a 2, 0, 0, 0, 0 and minus 1. This is minus 1 and 0. So, I am directly writing from here, this value should be 1 and this value we have to make as 0. So, with these manipulations it will be 2, 2, 1, 1, 0, 0, whereas this will be minus, sorry, not minus 5, 4, minus 5, 0, minus 4, minus 1 and 1. Calculate the Zj minus Cj, that is 5, 0, 4, 1, 0. So, in this case Zj minus Cj is greater than equals 0. So, this is the, we stop for this case. What happens now? Zj minus Cj is greater than equals 0, it is fine. So, we cannot, we will not proceed, phase 1 ends here. But look at the basis. The basis contains one artificial variable. My artificial variable was x 5 and what is the corresponding value of the artificial variable in the basis, that is in B column, that is 4. So, it is positive. So, please note Zj minus Cj greater than equals 0 and artificial variable is present in the basis with positive value. Therefore, for this problem has no solution from the earlier whatever we told, that if the artificial variable is present in the basis and its value in the basis is positive, then no solution will occur. The first problem what we did, if you note, in the end of phase 1 Zj minus Cj was greater than equals 0 and no artificial variable was present in the basis. We proceed for the phase 2, we obtained the solution for the earlier problem. For this problem now Zj minus Cj is greater than equals 0, but artificial variable is present in the basis and this is artificial variable is present in the basis with positive value. Therefore, we cannot obtain the solution. So, no solution exists for this one. Similarly, you can proceed for the other problems also. Let me just see one more problem. Just see this problem. Maximize z equals twice x 1 plus thrice x 2 plus x 3. This is little different, subject to minus thrice x 1 plus twice x 2 plus thrice x 3 equals 8, minus thrice x 1 plus 4 x 2 plus 2 x 3, this is equals 7, x 1 x 2 x 3, this is greater than equals 0. We want to solve it using the two phase method. Please note one thing, that here both are of the type, this one both are of the type equality constants are there. So, maximize z star, basically two artificial variables you will use here for both equality constants. So, it will be auxiliary function will be 0 into x 1, 0 x 2 plus 0 into x 3 minus x 4 minus x 5, subject to minus thrice x 1 plus twice x 2 plus thrice x 3 plus x 4, one artificial variable, and the next one is minus thrice x 1 plus 4 x 2 plus twice x 3 and plus x 5, this is equals 7, and x j is as usual greater than equals 0, j equals 1 to 5. So, two artificial variables are there. So, initial basis will be x 4 equals 8 and x 5 equals 7, x 1, x 2, x 3 are 0 over here. So, once it is 0, let us form the phase 1 of the table. In the phase 1, again your entering variables in the basis are x 4 and x 5, x 3 is 0 minus 1, coefficients are this, C B is corresponding to this is this. I am directly writing because this already you know. This will be 7 minus 3, 4, 2, 0 and 1. So, calculate the Z j minus C j, this will be 6, this will be minus 6, 5, 0 and 0. So, your entering vector is here x 2, calculate the corresponding ratio, this is 4, this is 7 by 4. So, therefore, outgoing vector is your x 5. So, x 5 is going out. So, in the next table therefore, you will have two things, one is a 4 a 2, that is x 4, and instead of x 5 it is x 2. Your C j is 0 0 0 minus 1 and minus 1. So, it is again minus 1 and 0. So, in this case your pivot element was this. So, I have to make this as 1 and corresponding to this row I have to make as 0. So, after the manipulations you can obtain the solution as 9 by 2 minus 3 by 2, 0, 2, 1 minus half, and for the next table it will be 7 by 4 minus 3 by 4, 1 half, 0 and 1 by 4. So, it becomes, if you calculate z by z j minus c j, 3 by 2, 0 minus 2, 0 and 3 by 2, still it is negative. So, your entering vector is now x 3. So, correspondingly calculate the ratio, that is 9 by 4 and this will be 7 by 2. So, the minimum of these two is this one. So, therefore, your outgoing vector is a 4, this is your pivot element. So, in the next table your instead of a 4 your a 3 will come and a 2 is already there. So, x 3 and x 2, your C j is here 0 0 0 minus 1 and minus 1. Your C b is then a 3 and a 2 is there 0 and 0. So, again I have to make this as 1 and this as 0. So, you will obtain 9 by 4 minus 3 by 4, 0, 1 half minus 1 by 4. This will be 5 by 8 minus 3 by 8, 1, 0 minus 1 by 4 and 3 by 8. If you calculate Z j minus C j, you will see that Z j minus C j is greater than equals 0 for all j. So, once Z j minus C j is greater than equals 0, so phase 1 ends here, and one thing should be noted that here x 3 and x 2 is in the basis. So, therefore, artificial variables x 4 and x 5 are out from the basis. So, we should obtain one solution. Let us see what happens. We should obtain one solution. Here in C j actually you will take the objective function, that is maximize z equals, you will take the original function 2 x 1 3 x 2 plus x 3. So, in this case you are taking the original data, that is a 3 x 3 and x 2, original table will remain same a 3 a 2, your C j value only this row will be changing 2 3 1, this is 1, this is 3, there is no change as such, 9 by 4 minus 3 by 4, 0, 1, 5 by 8 minus 3 by 8, 1 and 0. Note one thing, since the artificial variables are not present in the last table of phase 1 x 4 and x 5, these are not present over here. Therefore, we have dropped the columns for corresponding to x4 and x5 over here. Now, see Zj, what is Zj minus Cj? Your Zj minus Cj is, if you calculate, minus 13 by 8, 0 and 0. So, this is negative. Now, see here, whenever you are going to calculate the ratio, both the ratio are becoming, this is negative, this is also negative. And as we have told, if the ratio is negative or infinite, you cannot consider it. So, both the ratios are negative. So, in this case, we are having unbounded solution. So, although phase 1 the artificial variables were removed, but the ratios are negative and therefore, there will be solution, but the solution will be unbounded since both the ratios are negative, and we will stop here. So, various cases may arise. I think two phase method is clear to you. In the next class, we will take some special problems which arises in the simplex algorithm, as well as the degeneracy case, what happens, that we will discuss in the next class. Thank you.